All right. Okay, so we'll come back for the second half of chapter 6. So we are now looking at the hydrostatic forces. Okay, so under static fluid. Okay, static fluid is something important, as I said. So because in our daily life we are dealing with static fluid as well as dynamic fluid. So meaning as the water at rest and also water the moving water. Okay, so hydrostatic forces we will be studying earlier on the very basic level. Okay, now we're going to see in more practical way. So how the hydrostatic forces will be working. It will be a lot of derivation and a lot of calculations, but we are not really focusing on the derivation and also calculation. Maybe calculation a bit, but we are not really focusing on the derivation. So derivation, the steps I already gave in the lecture note, so you can just try to understand. So it's a basic mathematics, okay, but I will explain more on the theory part behind the submerged plane surfaces. Okay, so hydrostatics, we will enter into chapter 6.4 on hydrostatic forces on submerged plane surfaces. Submerged meaning is underwater. Okay, submarine is underwater vehicle. So similar, so submerged. So underwater there can be a lot of activities. Okay, so if let's say put a you throw a stone inside the water, after some time you can see it will go deeper. Okay, so when it go deeper, so what are the changes it will experience? What are the forces it will experience? So we will study in this part. Okay, so a plate such as a gate valve in a dam, the wall of a liquid storage tank, or the hull of a ship at rest is subjected to fluid pressure distributed over its surface when exposed to a liquid. Okay, so let's say you have a dam. So we always will see this. So we call it as a gate valve. So normally the dam will have a lot of gates. So gate one, gate two, gate three. So depends on the water level. So let's say if continuously raining and the dam is too full, they might open one gate, okay, to release the pressure. But throughout the process, so throughout the operation of the dam, so we can see the gate is experiencing a lot of fluid forces, okay, from inside. Yeah, because the water will keep on pushing to the gate. Okay, but so that's why you as an engineer you need to come up with proper calculation. So let's say you just make the wall with a tin plate. So what will happen after some time? So the it cannot withstand the force. So it must be a lot of layering, so a lot of concrete involved, so to withstand the pressure. Okay, so this kind of understanding is very important. Okay, on a plane surface, hydrostatic forces form a system of parallel forces, and we often need to determine the magnitude of the force and its point of application, which is called the center of pressure. Okay, so usually in the calculations, what engineers will check, they will check how much force, the magnitude meaning the amount of force it will subject to. So engineers normally will use the, so those time they do the calculation manually, but now mostly are computerized. So you just put certain values, so the computer will try to calculate for you. But still, we cannot forget the basics, because at times computer will just follow certain things, so there can be a miscalculation or something that very important you didn't consider. So which can, it will be case by case. So not daily you need to deal with uh, dam problem. Okay, so maybe it's something, a new phenomena is happening underwater, in the ocean. So you need to come up with a solution. Then you need to study it properly. So normally we need to determine the magnitude of the force. Okay, and its point of application. Okay, magnitude of force, how much force it will experience, as well as the center of pressure. So normally a body or object surface, it will have a center of pressure. So maybe the pressure is experienced throughout the body, but at one point it will be the center. So we need to, we call it as a center of pressure, or we call it as a COP, center of pressure. Abbreviation for center of pressure. Okay, so when analyzing hydrostatic forces on submerged surface, the atmospheric pressure can be subtracted for simplicity when it acts on both sides of the structure. Okay, so when we want to do the calculation, so let's say you can see from this picture. Uh, so let's say this is a container. So you have a water. So we know as it goes deeper, the pressure will increase. So this part we already studied in part one. But you can see on top part, atmospheric pressure is acting on the container body, and the other side, atmospheric pressure is experiencing. So meaning the atmospheric pressure here and atmospheric pressure here, it will cancel each other. So when you have this kind of condition, so this condition is not always will happen. Okay, like in a dam, it is not happening in the dam because you only can see one layer of atmospheric pressure. Okay, so this side maybe you don't really experiencing it. Maybe it's already properly covered. So in that case, you cannot disregard atmospheric pressure. But if let's say you are dealing with a container or you are dealing with a ship, where you can have atmospheric pressure in both sides. So you have a body. So this side body and that side body is experiencing atmospheric pressure. So then you can just take it up. You can just subtract. Okay. Then at the end it will be just be like this. Because atmospheric pressure here. So let's say here 100 kilopascal. This side is 100 kilopascal. So you minus each other. So it will cancel. Okay. But this case, yeah, this is this is after the subtraction. So you only have rho gh. Here you have atmospheric pressure. So you need to check on that. Okay, because when you subtract it, so you can make the the calculations simple. Okay, so we can see. So this is a practical application. So when you throw something inside, so let's say you are throwing a plate in the water, it won't go smoothly at the one angle until the bottom. It will normally go in a slanting way, then it will rotate. So a lot of movement can happen because of this force. So we need to understand the movement of the body first. Okay, so let's say your the body is at a certain degree. So degree of theta. Okay, this degree we are taking from the surface, and the direction is like this. Okay, so you can see. So I just explain first. So we have a centroid. Okay, so the body. So you have a cross section area. Okay, we call it as A. So plane surface of area is A. Then you have a center of pressure. Okay, this is the center of pressure. So center of pressure not necessarily have to be at the center. So centroid is the center of the body. Okay, so normally in Malay we call as titik imbangan. So even you take a book, you can balance it at one point. Okay, so even though the book is even or non-even, so at one point you can make it stand on your finger. So that is the centroid of the body. Okay, but center of pressure. is the place where the body is experiencing the most of the pressure. So that is what we call as the center of pressure. So we need to understand first thing, centroid and center of pressure not necessarily have to be same point, but in some case it can be same. It depends on the area of the exposed area of the body. Okay. Then we have some distances. YC is distance from the uh, plane of origin to the centroid. Then we have the area that we want to investigate that we call as Y. Then we have the H that we calculated earlier. We used earlier rho GH. So H here is no more a number. So we need to consider an angle because it's going in an angle. So y sine theta because this is the area that we want to investigate. So from line of action, so this is the distance y. So we need to take the sine component of it. Then we can get the vertical height, which is the h. Then we have a force Fr. Okay, the resultant force normally is equals to cen- uh, pressure at center times with area. Okay, so these are some of the values. Then on top here we have P0. So P0 is pressure at point 0 plus rho g y sin theta, no more h because it's going in angle. Okay, so these are the some of the things that we will be used in our derivation. Okay, so P0, so this is some of the legends. P0 is at on top, which is exposed to the atmospheric pressure. So P is absolute pressure at any point. So we want to measure at this point. So the density, so density of the surface under the fluid. And then we have the gravity and H is from this point to this point. Okay, the height. Okay, so we can use trigonometrics to calculate. Okay, so it's mostly on the mathematics. So that's why your understanding in mathematics is very important. So we cannot say, "Oh, I don't want to calculate. I don't want." So you need to understand all this. You don't expect me to teach in the class because this is supposed you already master it in your mathematics class. So that's why you are taking mathematics one, mathematics two, mathematics three, so that you will get used to integration, differentiation, which will be used in the subjects. Okay, so usually we will only deal with this, but now we are dealing with angles. So body at an angle. Okay, so if is just a normal analysis without the angle, then you can just consider this. Okay, so again, so you can see as it goes deeper. So this point and this point, so top, the one that closer to the surface is lesser pressure, and the one that is inside, so it's more pressure because generally the distance is different. So that is the reason why the pressure is not even. So usually the pressure will be more on the deeper side. So that's why the resultant force is downward. So at this point. So I just open everything. So this is some calculation, some derivation. Okay. So if you take all this point, okay, so you just take the information from this picture. So after you settle, you will know that the FR. So you can just go through the steps how you can get until this point. Okay, but at the end, I just want to focus FR or the resultant force at this point. is, so PC is the pressure at the centroid times with area. Okay, or the pressure average times with area. So this is the formula that we usually will use in our calculation. Okay, so if I ask in the exam, I will just give a scenario of a body entering submerged into the water, then it is experiencing a certain force. So you can straight away apply this formula. Okay, so Fr equals to PC times A, or Fr equals to average pressure times A. Okay, so and the derivation you don't need to really focus on. Okay, so the magnitude of the resultant force acting on the plane surface of a complete submerged plate. So the submerged plate also, it can have a completely submerged plate, so meaning it's totally underwater, or partially, so meaning some part is still above the water surface, and some part is merged. So in hydrostatic, you only need to calculate the part that is submerged under the water. Yeah. So it will be like that. Okay. So resultant or commonly used distributed force system. So normally in the calculations, so you can have this kind of setup. So now, if normal, so normally it will be like this. So it's uniform. So it's just like horizontal. The plane is horizontal. Then you can take the FR at the center. So if it's a triangular load, then it will be moving more towards the place where more bigger force, bigger pressure is applied. And if trapezoid, so it will be the same, because here the line is longer, so the force will be more towards the right hand side. Okay, so similar to you. Okay, so in this case, since it is a trapezoid similar like this, so it will be more near to the uh, place where the pressure is higher. Okay, so that's why it's not here, but it's a bit like down towards this side. Okay, so two parallel force system are equivalent if they have the same magnitude and the same moment about any point. Okay, so if let's say you are having two force, so two objects, so if it's at the same, it's experiencing the same magnitude of force uh, at the same place, same height, so we consider as a two parallel force system. Mhm. So the point of interaction of the line of action of the resultant force and the surface. Okay, so we call it as a center of pressure. Okay, the place where the force is applied, we call it as a center of pressure. Yeah, so the center of pressure is just the one point. So the force is constantly it's like an arrow. So the end of the arrow is the center of pressure. Okay, and this is the centroid of the area. Centroid of the area is like how I say is the balance point of a object. So like how you can balance a book using a finger. So the point where it balance, that is the centroid of the book. Okay, even a paper you can do that. So all the body which is subjected to gravity, it will have a centroid. So a balance point. But the center of pressure is the place where the force is applied continuously. So that is the center of pressure. Okay, so all these are some derivations. I'm not really going into this. So I just want to tell some of the important parts. Okay. Okay, so the moment, what we call as a moment of area, is actually the turning effect of force inside the water. So because once the body enters into the water, it will not con- be this at the same level. It will tend to rotate. It will tend to go slanting more. So all this need to be considered. So considered when you are measuring something. So moment is the calculation to find the turning effect of force underwater. Okay, so I'm not really going to all this. So it's more on the derivation. Okay, uh, the formula in rate. So we tend to use it when we are calculating all the turning effect of force. So what what is YP and YC? So we can get the information. Sorry, we can get the information from the picture. So I will show some example later. Then you can relate it. Okay, so normally the body that is exposed. So let's say it's a rectangle body, and then we can find the area of a square is AB. So A times with B, and the second moment of area for square is AB square over 12. So this is for square. So normally we will just take this formula depending on our calculation. Okay, so if the body is square, then we can take this values. If it's not a square, not a circle, but is more elongated, we call it as a ellipse. Then we will take this formula. If it's a triangle, so we will take this two formulas. If it's a semicircle, we will take this, and if it's a semi-ellipse, so we will take this. So we need to find which one representing the body that is submerged. Then we will get a better understanding of which one to use. Okay, so there can be a special cases where it's a submerged rectangular plate. Uh, so if it's a rectangular plate, if the question is saying it's a rectangular plate, then we can straight away calculate the resulting force using the formula given here. Okay. Okay, so this is the derivation for this formula. So it is from the initial formula Fr equals to Pc times with A. So Pc is actually uh, pressure at the atmospheric plus with rho g yc sin theta. So this is from the previous slide. You can so for to understand this this derivation, you need to refer back to the previous pictures. So like here, so PC, so you can see P0 is here. Rho is the density of the fluid, and G is the gravity. So YC sin theta. So YC sin theta is I want to show. Uh, so you can see here. So the YC, so YC sin theta. So point from here to here. So it will have a different point which will be used for the calculations. Okay, so this is a tilted plate. Okay, so HP is YP sin theta. Okay, so YP is point from the surface until the point center of pressure. So you are taking the sine of the theta. Okay, so once you replace it, so at the end you will get this. So this is the formula that we will use in order to find the distance of YP. Okay. Then we can have a case where it's a vertical plate. So vertical plate meaning once it's submerged, it's going vertically. So if vertically, we know that the top, the pressure at this top and the bottom will not be the same. So it will be lesser, down will be more. So the force will be more towards down here because it's a resultant force. Okay, so for this case, so we will use this formula here to calculate the resultant force. This is for to find the uh, height height from year to year, and IP from year to year we use this formula. Okay, then we can have a horizontal plane. So horizontal plane much easier because the pressure will be equal, and the force we can see is at the center because that's the resultant force. So and the force is P0 plus rho GH, P0 plus rho GH times with the area of the plate, okay, AB. Okay. So for this, so you can see the formula is much simpler because it's more direct. Okay, so hopefully in the exam you will be asked on this kind of horizontal plate instead of at angle, because when it's an angle, so you need to consider the angle of the submersion as well. So when the angle is entering the calculation, so it will be a bit like complicated because we need to find. But for your case, so you just need to apply, you just need to analyze the object and the object type, object size. Then you just need to use the relevant formula, which is already given to you in the rate font. So the rate fonts are the formula that we can be used. So if the questions will be given in the exam, so normally in the appendix we will give these formulas. Okay, so you don't need to like remember, but you just need to know how to use it to find the values. Okay, so a 6.5 buoyancy. So buoyancy is a natural kind of force acting in the water. Okay, so it's an upward force fluid exert on a body immersed in it. The buoyant force is caused by the increase of pressure with depth in the fluid. So we know as the object goes deeper and deeper, uh, there will be changes in pressure. So pressure will increase. So when the pressure increase, so buoyant force is something that opposing the gravity. So if let's say, so sometime when you jump, let's say you like swimming, you like diving. So when you dive, how after some time you can come back to the surface, because when you enter, when you enter inside, so the buoyant force from down it will push you upward. So this is actually is the upward force inside the fluid, and this is not happening by something artificial or created. This is a natural force. It's already available in the nature. Okay, which engineers can use to settle a lot of problems. Okay, plate, flat plate of uniform thickness H submerged in liquid parallel to the free surface. Okay, so let's say you have a condition. So you put this plate inside. So this is a submerged, fully submerged plate. So let's say this is the force acting downwards. So the force acting upward will be this. So this is the buoyancy force. So you need to take into consideration the thickness, because you will have two surface, top surface and bottom surface. The force acting on the top surface will be much lesser than the force acting on the down surface because of the thickness. Because uh, as it goes deeper, the pressure will increase. So there will be a slight differences. Okay. So FB, uh, so not Facebook. Okay, FB is buoyant force. Force as bottom minus force at top, because you have two surfaces that is exposed. So usually the bottom surf- surface, the force acting on it will be bigger. So bottom minus top. So you just replace the values, then you will get that the buoyant force is rho FGV. So the buoyant force acting on the plate is equal to the weight of the liquid displaced by the plate. So this is where the Archimedes principle is coming in. Okay, so let's say a body is having a weight, and you put it in uh, what a container with water. So the amount of weight coming out of the water is actually the force. So that is what Archimedes tried to prove. For a fluid with constant density, the buoyant force is independent of the distance of the body from the tree surface. It is also independent of the density of the solid body. Okay, so if the fluid is constant density, the buoyant force is independent from the of the distance of the body from the free surface. This is if the fluid is having a constant density. Okay, it is also independent of the density of the solid body. Okay, so this is actually depends on the density of the body. If it's a solid body, it will go inside. So if the body is not a solid body, uh, so olo inside, it will tend to go up because of the buoyant force. So that's the same principle that we are using on the ship. Why the ship can float? Because it's not a solid, even though the surface is solid, but inside the ship is hollow. So automatically the buoyant force will be higher, so it will push the ship on above. So that's why even though the ship is few hundred tons in weight, it can still float, and because of this principle. Because so solid, the weight uh, will be going downward, and the buoyant force will be acting upward. For fluid, also the same, but the magnitude will not be the same. So for solid, the downward force will be higher. The buoyant force acting on a solid body submerged in a fluid and on a solid fluid body of the same shape at the same depth are identical. Okay, so it doesn't matter. It doesn't matter whether it's a solid or fluid. The buoyant force, you can see the magnitude is the same, because this the buoyant force is depending on the height under the water. So different height will have a different buoyant force. So Archimedes principle: the buoyant force acting on a body immersed in the fluid is equal to the weight of the fluid displaced from the body, and it acts upward towards the centroid of the displaced volume. So buoyant force is acting upward. Okay, and Archimedes principle is saying, so when you put a weight into the water, the buoyant force is equals to the water coming out of the basin or the container. Okay, so for floating bodies, the weight of the entire body must be equals to the buoyant force, which is the weight of the fluid whose volume is equal to the volume of the submerged portion of the floating body. Okay, so for floating, Fp must be equals to weight. Then only it can float. Okay, so this is something related to the floating body. But what we need to understand is this picture. So is always will play with the density. If the density equals to the density of the fluid, so density of the body. So let's say the density of the ship, or yourself, yeah, yourself. So let's say you want to swim. So when the density of your body and density of the fluid will be the same, when uh, you are taking the fluid into the body. Okay, so let's say you are taking the you you don't know how to swim, you jump into the water, you drink a lot of water, so your density of your body will increase. And when it's the same, so it will be you will be like a uh, will be at the same level, so you won't go down, you won't go up, because your body is neutrally buoyant. So is the density of your body and density of the surrounding fluid is the same. But let's say you are a professional swimmer, so you know how to swim. So you know when you enter into the water, you shouldn't drink the water because of panic. So you enter the water, you close your mouth, and you're not breathing. You control your breathing. So the water is not entering. So because your body cavity, your body is designed inside is hollow, so that your density of your body will become lesser. So it will be lesser than the buoyant force. So automatically your body tend to float. So if you know the swimming, swimming, so you'll understand what I'm trying to say. So this the same thing happen in the ship. The ship inside you make it hollow, so the density of the ship, even though is the weight is bigger, it still can float in the water because you are designing it that way. And if is sinking, sorry, okay. So if you are sinking, so let's say a submarine. So submarine can be a good example. So if the submarine you want it to float, so submarine will normally will have a two deck. So the top deck will be for the people to stay, and the bottom part you have like a water detention tank. So if you want the submarine to submerge, uh, the submarine pilot, they will open the valve so that the fluid will enter the submarine into the tank. So when the water comes into the tank, so the submarine will have more weight. The density of the submarine will increase, and it will go down. It will start to sink because the density is more. Because the density of fluid plus with density of the submarine, so it will start to sink. So once it reach certain depth, so you don't want it to sink further, so you just throw out the water a bit. So once the density is equals to the density of the fluid, then it will start to suspend. So it will start to maintain at certain level. It won't go up, it won't go down. Then you can use a propeller to move in the water. Okay. And after some time, you want to go back to the surface. So you need to have the understanding that you need to throw out all the water from the detention tank. So once you throw out the water, so the submarine will come to the surface. So that is how the densities will help you to float, suspend, or sink in the water. So this is the same principle we are using in the daily life when we swim. So when the ship is going floating on the sea, and also for the submarine. Okay, so that is some understanding about static fluid. So I just like want to quickly go to one question. Okay, so that you can get some understanding. Okay, please hold on. Okay, so chapter 6 example. Later I will upload this. So I just discuss one example. So I give two example here. So we just go through one example. Okay, so this is the example and how we can use the previous known formula. Okay, so example one, every car plunges into a lake. So lake we know is a static fluid during an accident and lands at the bottom of the lake on its wheel. Okay, so let's say this is the lake and this is the bottom. So the car made an accident and it start to sink in the water. The door is 1.2 meter high, okay, and 1 meter wide. Okay, so they give some dimension, and the top edge of the door is 8 meter below the free surface of the water. Okay, so from the free surface until the top of the car is 8 meter below the free surface. So determine the hydrostatic force on the door and the location of pressure center. So location of COP. Pressure center is center of pressure. Okay, and they asked to find the FR and also COP, and discuss if the driver can open the door. Okay, so uh, inside the car, so there's a driver. So he became let's say he became unconscious because of the accident, and suddenly he awake. He already underwater. He tried to open the door. So the question I asking to discuss whether the driver can open the door. Okay, so we will see. Okay, so the average gauge pressure on the door is the pressure value at the centroid midpoint of the door and is determined by. Okay, so we know. So average pressure is at this point at the center of the door because we want to check whether the driver can open the door or not. Okay, so we know from the previous slide. So later you will check back with the slide. because if I open the slide, so I will go out and come. So I just do one. I just take the this formula is from the previous lecture, so you can get this formula. So average pressure here is PC, so pressure at the centroid uh, equals to rho g h. So since this body, so earlier we saw, right? So the body as a vertical, body at the angle, and body at the horizontal. So body at the horizontal, so it will be experiencing the same force throughout the body. So it's easier to analyze. Okay, so we know, so P average is rho g s plus b over 2. So s is 8 plus so b is so this distance, so 1.2, so 1.2 divided by 2. Okay, so rho is 1000 because it's lake and they say it's a water, so we know that it's 1000 kilogram per meter cube. So gravity is 9.81 and hc is 8 plus 1.2 divided by 2, and this is a unit conversion. So after you solve, you get average pressure is 84.4 kilonewton per meter square. Question asked to calculate the hydrostatic force. So hydrostatic force, we use back this formula already derived before this. Fr equals to average pressure times with area. Okay, so average pressure is 84.4 kilonewton per meter square times with area. Area is, so assume this is almost like a square. So 1 meter times 1.2 meter. Okay, so if you consider like this is not a square, so you just write a statement there. Assume the door is a square, so then you can use this. So it's not wrong. So 1 meter times 1.2 meters. So once you solve this, we know that the force acting on the door is 101.3 kilonewton. Okay, so we already found the hydrostatic force. So now we want to find the location of the center of pressure and we want to see whether the driver can open the door. Okay, so the pressure center is directly under the midpoint of the door. So we know the midpoint of the door is here. And its distance from the surface of the lake is determined. So this from the book, equation 7.9, by setting P0 equals to 0. So you only want to consider the gauge pressure. Okay, so this is from the previous slide. So Yp equals to S plus B over 2 plus B square over 12 S plus B over 2. So this is already derived for you. You just need to use it. Okay. So S is 8 from distance from surface to the top. So B is 1.2 over 2 plus the B. So you just replace S and B inside. S is 8, B is 1.2. So you replace it inside here. Then you will get this. Then after you solve, we know the value is 8.61. So the distance from the surface until the midpoint is 8.61. So we know from here to here is 8. So bit like down here is 0.61. So total is 8.61. So we already know the location of the pressure center. So which is 8.61 meters from the surface, water surface. Okay, so we already settled these two. Now we discuss whether the driver can open the door or not. Okay, so this is a discussion. So basically on the assumption, so a strong person can lift 100 kilogram, which is a weight of 981 Newton, of about 1 kilonewton. Okay, so let's say a person so if the person can apply the force at the point farthest from the inch 1 meter farther, the maximum effect and generate a moment of 1 kilonewton per meter. Okay, so let's say the person can lift 100 kilogram, but if we convert to weight, so 100 kilogram is mass, so it's not a weight. So if you want to convert it into weight, you need to times with 9.81, so which is almost like one. We assume it 1 kilonewton, so 1000 newton. Okay, so if the person can apply a force, so maybe like 1 meter, so you need to generate a moment of 1 kilonewton meter. Okay, the resultant hydrostatic force acts under the midpoint of the door and thus the distance of 0.5 meter from the inches. So we know it's 1 meter, so we take a center. So if we want to open, so we need to push at the center. Okay, so we know the point is 1 meter divided by 2, so 0.5 meter from the inch. So normally the inch will be a where the door will be connected to the body of the car. So if you want to push, you push at the center. So these generate a moment of 50.6 kilonewton, which is about 50 times the moment of the driver can possibly generate. Okay, so the driver maybe he can generate uh, one one kilonewton per meter, but the door at this depth it generate 50.6 kilonewton. Okay, which is 50 times higher. Therefore, it is impossible for the driver to open the door of the car. So because the moment at the bottom of the lake is 50 times higher than what he can do. So let's say he can lift 100 kilo. So let's say he can lift 5 ton, 5,000 kilometer, then maybe he can open. And because it's too far in the lake. So the driver best bet is to let some water in by rolling the window down a little, for example, and to keep his head close to the ceiling. The driver should be able to open the door shortly because the car is filled with water. Since at the point of pressure of water, sides the door are nearly the same, and opening the door in water is almost as easy as opening the. Uh, so this is another knowledge for us. So if normally what we will think, if I let the water come inside the car, so I'm going to suffocate and die. But in this case, so let's say it won't happen. It won't happen. But if it happen, so normally what we will encourage, so we will ask. We maybe it's impossible for us to open the door because of the outward force acting on the door. It will prevent us from opening the door. But the more fragile place will be the mirror. So either you kick the mirror and make it a break, or you can take the eight rest. So eight rest you put at the middle point at the door. So you push and you break the mirror and you swim out. Or here they give a suggestion. So you open the window little bit. So you open the window, let the water enters the car. And because somehow you cannot save the car, so you need to save your life. So since the moment is 50 times, meaning the force is 50 times more than what you can endure, so you let the water come inside first. So when the water come inside, the water will be pushing, will have some force acting on the door as well. So meaning you are assisted. So you provide 1 kilonewton, the water come inside will be same like outside. So it will have, you will have another 50 kilonewton of force from the water inside. So you just like maintain your head high. So don't let water come inside you. So you, with the help of the water, so outside force is 50 kilonewton meter, but inside you will have 51 kilonewton meter. 50 from the water, one from you, so you can open the door easily and you can swim up. But you need to do it in a very fast pace. So you cannot take like 10 minutes to do all this. So of course you will die. So you need to do this in matter of seconds. Uh, so in matter of second, so you determine at the time. So whether it's better to break the mirror and swim out, or you let the water come inside and you open the door and you swim out. So the choice is yours. Okay. So that's about it. Um, so you have another example. So you can just go through later. I will upload for your understanding. So you just can go through. Okay, all the steps are given. Okay, so that's all for today. So I will take attendance. So any questions before we finish? You have another 3 minutes. So any questions? So if no questions, I will just end the video.